Okay, so yeah, hello. Okay. I'll share my screen, then we can start. Okay, so um, okay, we can start, right? Uh, so today we'll cover week 9 and like week 10 also. If you have a doubt, then have it. So week 9 contains how to if you have text kind of data, how can you um, do something with it so that you have word representations, right? So that is the whole idea behind week 9, that you want word representations. So, uh, let's say a sentence that I am going, right? So this is a sentence. The easiest way is to convert it to one hot vector, right? So you can represent I as maybe like this. This is one vector, and then let's say M can represent as 0, 1, 0, and going as 0, 0, 1, right? So this is the uh, minimum list effort way to create a vector from words, right? So this is what one hot vector is. But the issue is they all are orthogonal, like they they are not related to each other. So let's say I might be along this axis and I'm going to be, let's say, along this axis, and then the going will be along the other axis. So they are not. We can't figure out any relationship between them, or are they even? Is there any point of having them together or something like that, right? Uh, so we are losing some meaning, semantic meanings across this. But so let's say we have dog and cat or something like that, right? And then truck. Now we want maybe this two to have similar or maybe near vector, right? So this vector is a representation of dog. Then then you don't want cat to be orthogonal to it. You might want maybe a little bit nearer to dog. So that is the idea that we want word representation. So one thing you can do is you can apply SVD and you can have better word representation, right? So this one hot vector, you can take this thing, the whole matrix, apply SVD on it, and you will get three matrices. So this is one matrix. You do that, and you'll get U, sigma, and V, uh, kind of this V transpose or something, right? So this you'll get three matrices, and then you can have uh, approximation up to some strength, right? So let's say you want one or two or something, right? So U1 sigma 1 V1 transpose plus. So you can have this much, or if you want better or more less error, then you can add more and more components, right? This four components, like maybe um, whatever the size of it, right? So this is M cross N, then this is going to be maybe let's say n cross k, and then this could be k cross k, and then this will k cross this should be m cross k cross n, something like this, right? Uh, so it will be like this, right? This was the easiest way, like SVD way. I'm not going much into it, but the next part is like where difficulty comes up is uh, so this is where we'll not use any kind of learning happening, right? Like machine deep learning. There is no weight parameter or anything in SVD part, but in next thing, which is let's say the skip gram uh, or continuous bag of words, right? So uh, so what are these? Actually, these are fake problems. Uh, by that mean is, let's say I have word I am, and I have to predict what is going to be next, like going, running, walking, eating, something. So these are the next word which I want to predict. This is this is one fake problem. Like we don't care about this problem actually. What we actually care about is while solving this problem, what kind of a matrix will come out which will represent this all words, right? So this words, how it will represent it, right? So this is what I actually care about. I don't really care about this word, but this problem is required to build this um, objective function and all, so that we can get this word and context vector, context matrix, right? So so that is the idea. Another could be so this is one that we have given the uh, we have given this words and we have to predict the context, right? So one is that, and another is like given a context, predict the word, right? So let's say all the words are given around it, and then you have to predict the middle word, right? So this is also another problem. So uh, yes, right. Mhm. So so this so in research paper, the thing which is this if we do have a words and we are trying to predict the next word, this is being done using continuous bag of words, and this task can be done using skip graph, right? So um, all the around context is given and then predict the word, right? So this can be done using skip graph. Now so now what we have to do is actually we have to um, uh, so so whatever words are given to you, right? So let's say a vocabulary is given to you. You will do what you'll do is you will create the one hot vector of that, right? So one hot vector creation is easy. That whatever words come up, something you create, right? So like we did here, that this is a one hot vector representation. So that's what you have to do for all the vocabulary. Vocabulary means all the words in the your corpus, right? So corpus, uh, you have several text and whatever is there, all the words you take and you create a one hot vector of that, right? So that's what you have to do. That is the initial part. Then what you will do is you'll just train a feed forward neural network. That's all. Like uh, so let's say this is my input layer. Fine. Um, uh, and then let's say this is my hidden layer. Okay, you can have as uh, larger you want. But what we generally assume is we'll have so V is the size of vocabulary, then we should have lesser number of neurons in it. Okay, then the V. So that whenever we get a W matrix, W is going to be the weights in between this. It's not going to be V cross V, but some lesser size. Right? So that's what it helps. Like we have this size as um, so if I do with uh, one hot vector, then um, then the size is going to be V cross V, right? The metric size is going to be V cross V, all the vocabulary words. But we want to reduce it to somehow, right? So that reduction of thing is you can do this way. So the number of neurons will actually define the reduction, right? So this K or D or whatever. So you can choose number of neurons here, and you have weights, right? So let's say one vector is represented as 100, and then some weights are given here. So that W1 or whatever you can call it. So here it is W context. Okay, and then you'll have output, right? So that is the last layer. This is the output layer. Of course, it has to be same as the words present in your vocabulary. Right? So this can't change. It has to be of V size. Okay? So this has to be V size. First layer, last layer has to be V size. The middle layer has to be of smaller size than V, so that we can represent a word using uh, lesser numbers in a vector. Right? That's why this is a K. And output, of course, is a classification problem, right? Because uh, the ideas we wanted the, let's say, probability distribution, right? So that is the good idea that we use softmax here. We can use softmax here. In middle layer, we can use anything, sigmoid, 10H, or something like this, right? So any activation function we can use, which are a little bit non-linear, right? Like ReLU and all, uh, not advisable. So most like sigma and 10H are being used. So how many elements are going to be in the W context, right? And let's say here is W word. So how many elements do you expect in W context? This is the W context, blue one. Right? Uh, this is weights between my input and the hidden layers, right? How many elements do you expect to have it? Let's say this is V, this is K, right? So, uh, am I audible?
Yes, sir, you're audible.
Okay. So do you get the question?
Yeah,
What I'm asking?
in the context layer, the number of neurons.
Yeah, number of neurons are K. So here K is there, and hidden layer, and here the number of neurons are, or input neurons are V. So how many weights do you think will require to connect the input and hidden layer? Input and hidden layer. Feed forwardness, right? Normal. There is
So it's
nothing.
it's V plus K. V waits for V and K waits for K. V plus K. No?
No, right? The so let's say first we'll go to first one, then second will go third, fourth, right? All the points will go. That's
So
how
each neuron will have one weight and one bias. So they are V neurons. So V weights. No?
each neuron will have V, correct? V, each neuron will have V weight, and one bias. That is correct. So we have, so how many elements are going to be in W context matrix, right? So this is a matrix W context. Uh, what is the size of it? What do you expect the size of it?
Um, K, because they're K neurons, so K cross,
V, right? K
yeah,
cross V. Okay, so that's what it is. And then how much? What is the size of W word you are expecting? Um, output is also V size because all the words we want to include, right? By
yeah.
prediction.
They have to be V cross 1 because all the words are V cross V into V cross V. I don't know. There are V words in
V
the
cross
V,
K, right?
V cross K. Okay.
W word. So this many are the weights required, and of course biases are there. So as many neurons here, so three K neurons, right? So K biases for this one. Here like maybe K cross one bias, and here for softmax will require V biases because there are V elements here, right? In the last layer. So that's how um, the structure of the continuous bag of word is. The idea is that we want to create this vocabulary, or we want to create X and Y. That is the only new thing, X and Y, that you can create using all the words given to you, or all the vocabulary corpus given to you. So you will have, let's say, I am, then uh, then the next one is output is going to be going, right? Then there could be, let's say, he set on, then here could be chair. Now I get that sometimes it's not going to be uh, like, uh, same, but you have to make it same, right? So that is the idea, that you have to choose the window size, that how much context you are going to take to get it. So here I've taken context size is 2. You can have it any number, right? 3, 4, 5, doesn't matter. So that's also he set. Then the next prediction word could be on, right? So like this. And if I have given set on, then the next prediction is chair. So this is X and Y that you have to create using your corpus. If you have this, then there is nothing new. There's just a feed forward neural network, and you do back propagation, right? So loss function is going to be uh, the usual loss, like right, cross entropy. You can use that, right? So if you have that, then you just have to back propagate, and whatever weights at the end of this, the whole training period, or whatever you get at the end, those are those are the metrics will be used to represent the words now. Okay, fine. So this context vector we can use as a new embedding. So now we'll call them as embedding. This is called embedding. Are they better than V? Any um, anything good about uh, this W, which was not there in V cross V, this thing, right? V cross V, um, or what, co-occurrence matrix. Um, you can use co-occurrence matrix also, but here I use one hot matrix. You can use co-occurrence matrix. That is also okay. Mm. So size is reduced, right? So now let's say I required, let's say if I have corpus or vocabulary size as 10, that's I am going, he sat on chair. How many? 1, 2, 3, 4, 5, 6, 7. Okay, let's say 7. Okay, 7 I have. Then I can represent like this, right? So this is one way to represent I, and only ways. And then M I'm going to represent like this. So this is one vector. So if I write all of them, you will raise this matrix will be of size 7 cross 7. If I do apply SIBO, which was above architecture. If I do that, then I can have it in any way, right? So if I can have it, let's say 7 cross 3 or something like that, right? That is the idea that I'm getting k cross v, right? So 3 cross 7, that's a 3 cross 7. So all the columns, right? All the columns now I'll say that that is being represented by three words, right? So, or you can see that I am representing as same thing on the right. There is nothing difference if I write row wise or column wise here. And same thing here. There's nothing, not much difference in CBO. Now, the idea is you'll get two kind of metrics. One is context and one is word, right? Um, and so mostly we use context only for the usability. Like now we wanted to. So now we got the word represented, and we have to do something about it. This was the basic or primary step to get words and numbers. Now numbers we'll use to do classification or some kind of task, right? So which one to use? So generally, most likely we'll use context, but you can use word as well. There's nothing different about it because uh, uh, like what's happening is the intuition. Um, that's what sir is also saying always, that the intuition is that, let's say dog is related to eating, and cat is also related to eating, right? So let's say this is the context. So dog and cat are coming near, as well as cat and eat are also coming near. So there is a good chance that that this all three of them could be near to each other, right? So that's why if you use word, context or word, the output doesn't change much, right? It will not affect that much. They all could be very near to each other, right? So this word contains in different way the vector is represented, and in context, same word is represented in some different vector. But if you see dimensionally, they are going to be near to each other only if they are related to each other, or they are coming in the same kind of words, same kind of sentences, right? So that was SIBO. It was simple that you have to create this feed forward neural network to web propagation, and you will get the um, word representation. Is that fine? Um, is that okay? Is there mm, anything else you want to?
How do we extract context? Like, what if we take top three? So seven is okay, but if we take only three, then won't there be repetitions in that 3 cross 7 matrix? Because some would be like 0 0 0 because it's the
No, no,
whole.
there it won't be 0 0 after. So currently it is sparse. See, we are sending a sparse matrix, but what we are going to get is dense matrix. It's not going to be uh, zero or something like that. It's always going to be dense.
Okay. Just
Okay.
once again, how are we generating embeddings from words? That part.
So this word context, W context is the embedding now. That thing is
What's
embedding.
the mathematical formula to get W context from a bag of from first we take a body of text, we identify the unique number that is V. Then from V, W context is predefined. Or do we
Uh,
identify that the nearest word should be the context? Uh,
no, no, no. See this. So actually, see what we are doing is, let's say I am or I is represent like this. This is I, right? So after you do this whole thing, you will see that word W context, inside W context, one column of I is being represent like this 0.28, 0.52, 0.3. So now the size could be lesser also, right? Like that's what we saw, 7 cross 3 above. So here maybe like that. It has reduced. I'm showing one only, and that same thing will happen for all the words, right? So here I needed four numbers to represent a word. Here I'll require three numbers and they are dense. They are
No,
not
sorry,
sparse as well.
I missed it. How did we get this point to it? Is it sigmoid?
That's no. This is W context.
Okay. Okay.
So this is I'm showing inside what is inside W context. This is
Okay.
the one hot, right? So I'm showing how W context might look like. I'm representing as rows, but mostly the architecture we drew it's column wise. So let's say like this value was um, 0.4 something. Right? So this is how now it's being represented. It could be 2.3 anything. Okay, not
You should not
necessarily.
sum to one. It's not a probabilistic thing that all should
Uh,
sum to one. Okay.
so no, there is no necessity for it to sum to one. So these are words. So let's say you do just think like you have normal ANN, right? Artificial neural network. Uh, Weights could be anything, right? There is no limitation to what a weight could be inside ANN. Same thing here. Those are the values. The weights which we were earlier having now, those weights we are calling as W context or W word in the next metric.
Understood, sir. For example, so that clarifies my doubt. So what I thought was, suppose if there are two statements which says that suppose Ram is going, or say X is going, and the second statement just says X, or say he is a cricketer. You should
Hmm.
know what is the context. So that means where is he going? He must be going to cricket field. So then context, I thought context is dynamically calculated from the words in the order in which they
Uh,
exist. Just like in large language model, they
no.
predict the
See,
next. Yeah.
what you mean is semantic meaning of the sentence.
Yes.
So this model is called CBOW, which is continuous bag of words. So continuous bag of words means you have this bag, right? Bag, and inside this all the words are there. They have no order. There is nothing related to each other. You can't compare them with like I mean
Understood.
uh,
So there is no order. There is no like the nearest word is more important than the
yes,
word.
yes.
Okay,
There is
understood.
not. But the idea is now we are getting the vector in similar directions. So the words which are maybe related could appear in similar directions. That is the only thing we can get out of it. There is no the order of words are not affecting. But yes, you uh, in which direction they are going. So we can say they are near to each other or they are related to each other. Relation we can maybe related we can figure it out, but not the order of the words, right? So sometimes order does matter. Like uh, what I'm talking about. Am I saying this thing first or after it? So that will be covered in RNN, right? That sequence of the if sequence is important, then we can use RNN. So that is the next idea about it. But here sequence is or order is not matter, but relation is kind of preserved.
Yes, sir, understood.
Okay. So that was the bow continuous bag of word. Another is skip gram. So in skip gram, what we do is we are given, let's say I am going let's say dash supermarket, something like that, right? So we have to predict what is going to be this word, right? This word. It's going to be to from or something like that, right? So out of several words, we have to predict, and of course, we'll get the probabilities of it, which is going to be here, and we'll take the most probable word to be here, right? So that is the idea. So in this also, what we do is we generally take a window size. So we have this corpus. Let's say this is my sentence. This is my corpus. I take a window size of uh, let's say 3. Okay, for example, I'm taking 3. So let's say it starts here. Okay. Now, how I'm going to create this corpus is I and going is there. Then my prediction is M because that is the uh, label, right? then I'll shift my window to 1. So this shifting you can decide 1 to how much you want, right? Um, so if I shift by 1, then it will shift to here, like this. Then M2, then my prediction should be going. And same way, it will go to next point, like this. Uh, this going and super market, then prediction should be 2. Now, so generally what we do is we always initialize these sentences by some starting. We give it that this is my starting point and this is my ending point. Okay, ending. So you'll see that most of the algorithm starts not from here but like this. So like some starting and M, then my prediction should be I, something like this, right? So you might see this. So that we are not missing out this word, right? So first word we have to give, then the next prediction can come up, right? So that is the idea. So this is now these are my feature or X, I can say, and this is my Y, right? Now I want to predict this. So how can I can how can I do it? Or actually I'm doing other way around. This is X and we want to predict the context out of it. Sorry, I think I missed. I said incorrectly earlier, but um, this is X. So one word is given. What could be possible around it, right? So M is given. If this word is given, then what is the probable word around it, right? That is what we wanted to predict. Another way. So this is also another fake problem. This both are earlier one also fake problem. This is also fake problem. We actually don't care about this problem or to solve it. We actually care about the word embeddings we are going to get out of this, right? So finally, um, we'll move to we will not have this one hot vector, but we'll have better embedding of this. That is the idea. So this is skipgram. In skipgram, what we have is same thing. Like there is nothing different I'm doing. We'll have similar input layer, uh, hidden layer, and then output layer, right? But this time I'm predicting context. So so what we'll do is let's say I give um, I as input, right? Or M as input, then my prediction should be I uh, and going, right? This 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 two should be my prediction, right? Um, so in output I'm getting like if given M, what is my predictions, right? If given M, what is the prediction of going? If given M and 2M, then this supermarket or something, right? So these all predictions have come out, and I have to choose two of them. So I'll most likely have probability here and here, right? Higher probability. So I'll have both of them. I'll choose and I'll give the context of that. So now this is called W context, and this is what W word, and prediction goes same thing, right? There is nothing new I'm doing related to the previous thing. Same forward propagation, backward propagation. Size is, let's say this is K, this is V, this should be also V, right? Uh, do you get it? So this is what skip gram is. Fine. Um, Same thing as earlier, just I have to take more words on in prediction. Earlier I used to take one word because I required one only, next word. Now I want to predict two words, so I'll take two of them, both of them, like right. That what could be the context of now. It could be we might not get the best thing around it, but that is okay. It will automatically learn and update it. So let's say in first round it will might say uh, going I. This could be the word in first run. Then we'll have more words like this, right? So it will learn and finally it will do correct prediction. Uh, so automatically it will happen. There is nothing we can control about it. So this will happen eventually. That is the whole idea about backpropagation. And we'll have this both the word and context, and we can use context as a new embeddings. Right? So the new embeddings are going to be the sub W context or the columns of it. Right? Uh, I guess that's okay. Um, now, okay. Uh, okay. So we covered skipgram and CBOP. Now there are several various uh, variation of this. Like let's say two word is given, three word is given. Then how can you do? And that all right. So if you watch the lecture, I think you'll be able to understand it. I believe it's okay, right? Uh, any, anything else you want me to cover beyond this? Should we cover RNN or anything like? Uh, do you want me to have session on another time? Uh,
Yes, sir. I think because nobody is joining here, it's only three people here. Maybe we can reschedule it because week 10 and 11 are coming together next Sunday as deadline. It will be even difficult to cover. And then we have two more Sundays. We have before 13th of April, we have one Sunday.
uh, that is correct.
Yes, so before 13th of April, we have 11th, which will be the revision, and 4th. 11th, 4th, and 28th. So we have after this we have only three sessions before enter. So one is gone for revision. So we will have two sessions for 10, 11, and 12.
So uh, so you want um, another session is going to be
Yeah, maybe next week
24th.
we can make it larger if the attendance is more. Maybe an
So
hour and a half, and then you can give the time back.
okay, so you want session or another time, like same week
I am
session?
available to be very honest with you. We can put it on the group that which nobody joins, so we are dropping off. And we can do a poll that if they have some time on the weekend, we can do it. Else we can have a longer, next we can cover 10, 11, and 12, three in one. But then after that, we'll have
No,
only
no.
one.
See, covering is not an issue. I mean, covering, okay, lot of content is not for the time wise. Uh, but the idea is if you have doubts, you can ask. If you don't have doubts, then uh, there's no point going on, right? It's just don't see point going on because lectures already there. Most of the students, if they are able to understand it,
So if you
then
can solve one of the practice problem, I can tell you which one. When I was getting stuck, week 9, that will be very helpful. Those who are also watching the recording, the practice assignment 9, uh, I think number 7, the formula for forward gradient descent formula. That, that will,
so actually, okay, this one is given in the lecture itself. Like, uh, there's nothing you have to do. It's given in the lecture. Like, you just watch it. He's explaining it. The prof is explaining it. Straightforward
yeah,
question.
why it is plus, I could not understand. I thought it would be negative. Like W transpose W minus theta is positive. That's the reason I was
So actually, this is not. You are using it in train. It's given by. So so. Uh, So idea was that if let's say WB or a V this VW has become 1, then there is no need to do any back propagation. But if it is 0, then the next one will be there, and then you have to do the back propagation. So 1 means you got the vector which you really wanted, like the true vector you wanted, like there is no error, and that's why. So this is not actually the plus is coming because inside there is subtraction going on, right? So something you add and something you remove, like that. So uh, this negative part is still there, but it is inside now, right?
understood. So I'll go to the lectures.
Yeah. So it's given like why it's happening. What is the intuition? I think Prof is clearly explaining it. This part at least I remember. So it would be great if you go through that. But I get it that this W word in context, how it is coming, it might be difficult, but that is normal ANN. There is nothing new about it. It's simple. This is the architecture, and that's what he is doing. It's just the new diagram may be overwhelming, but there's nothing new about any of this uh, algorithm. Okay. Uh, uh, so so what we can do is what I would suggest to any of you is uh, maybe you can have a post on discourse or somewhere that this is the topic I am feeling difficulty and can you cover in next session. We can do that, right? That is a better way uh, to go ahead if you have some difficulty.
Sure, sir.
Yeah, fine. Okay. We want any session in between, like not before, like not on next Friday, but before that. Is it? Uh, is it like can you, if you want, you can initiate a poll on which day, what time, and on discourse and tag us. Chakra, I will be able to take it. If it's in evening and not on Thursday, then I can take it next Thursday. If it's not then on except Thursday I can take the session. Evening Thursday, except Thursday I can. Uh,
Sure,
yeah,
sir.
fine. Okay. So okay then I think your time also. So I think we can close the session.
Yes, sir. Thank you, sir.
Yeah. Thanks. Bye.